Hello, we're going to have a look now at AQA Physics. We're going to have a look at this topic by topic, taking us through each of the topics one by one, and we're going to start with having a look at conservation and dissipation of energy. So let's get to it and have a look. And we're going to have a look at the different sort of types of energy stores that we can expect to meet. So energy is stored in a whole variety of different ways, and we need to have some idea about what these are. Right, so energy stored, first of all, then, as chemical. This is probably the most used of the stores. Energy is locked up in items like petrol, coal, and we use that to power all sorts of things. But also it's locked up in things like glucose, the food that we eat. We've got energy really locked up in a whole lot of other things, and a popular one there we think of is nuclear energy. We've got the atoms storing up the energy for what we want to try and use. We've got energy of height, so we literally lift something up. My example here is I can lift my rubber up. It's got energy, and when I let go, we lose energy. And this energy is changed from one thing to another. It's changed from movement into sound. So we've got GPE, gravitational potential energy. And if we've got that one, then we can also use another one, which is elastic potential energy. We can store energy up in a spring, or in that case, a rubber band. So we'll call that E potential energy for elastic potential energy. Can just be done as EPE, just as the other one here can be done as GPE. We can store energy up in, not quite store, but use and see energy stored up in electric energy. And we can see it in solar energy. And the worst of all, I suppose, we see them as thermal energy. Thermal energy is, if you like, the weakest of all these and what everything normally comes down to. We also saw sound energy. We also have light energy, and I'm sure that you can probably think of a few more. Basically, when we look at all these forms of energy, we have to remember a certain rule. And that is that energy can neither be created nor destroyed. We can change energy from one form to another, but that's about it. So let's take this rubber. We can raise it up. It's now got gravitational potential energy. I let go, it moves. That is kinetic energy. And then that kinetic energy turns to sound energy. So I can have my hand, it's going to lift it up. So we've got the chemical energy in the food that I've eaten. That has been turned to lift my hand and the rubber, so that turns to gravitational potential energy. That is then turned, as it's dropped, to kinetic energy, and that kinetic energy is turned largely into sound. Maybe it got a little bit hotter. Maybe there was a change of shape. And energy was required to change the shape of some of the molecules, which is, again, chemical. So energy changes are all around us. The most common one to see is gravitational potential energy turning into movement energy, kinetic energy. We can look at this with a variety of different systems. One of those that you may be familiar with is to show how kinetic energy can be turned to heat. And we get that if we take a container and we shake it and put a thermometer in there and it gets hot. I decided not to do that experiment because it just makes so much noise that I decided not to. But I'll put a link in the description below so you can see that experiment. So we can do the beads experiment, and we shake beads and they get hot. And that is a way of showing how energy is changed from one to another. So this conservation of energy is vitally important to us, and we can do all sorts of things and experiments to try and show this, and we'll have a look at some of those. Got the wrong button there. Right, so conservation of energy. We have to remember that energy cannot be created, it can't be destroyed. And this applies to all energy changes. Now, some people start to argue some of these things, and it is possible to change matter into energy and so on. But in the normal physics lab, I don't normally have access to a thermonuclear bomb, and I don't normally set one of those off to try and change some matter into energy. Generally, if we've got a closed system, then things can't escape. And if we have a look at a closed system, we'll put a box around it, and then if we try to change one sort of energy into another, so let's take a very simple system. I'm going to take a battery, I'm going to connect this to a bulb and then back to my battery. I've got chemical energy is going to be turned into electrical energy. Chemical energy is going to be turned into electrical energy. Electrical energy is then going to go to the lamp, the bulb, which is going to turn that into light energy and into heat energy. And none of that's going to escape this system. And all we're going to see is something getting a little bit basically hotter. The light energy will radiate onto this enclosed box, I suppose, and the box will in fact itself heat up. So our chemical energy is turned into electrical energy. Our electrical energy turned into light and heat, and the light will eventually turn into heat as well when it hits the box. And so all my energy has been turned into heat. And it's gone from being fairly concentrated to very spread out. And when the energy is very spread out, it's very hard to do anything with it. So the energy can be transferred from one system to another, but in a wider system where I take just my battery and I take my bulb, then we see this light energy as being lost, because this light energy, if you like, carries on virtually forever, gradually getting more and more spread out and lost, I suppose. So it's only lost to the external world. It's not done to any other sort of system. Right, so there's our idea of energy systems. Now, what we can do with this then is look at bungee jumping, not one of the easiest experiments to try and show in the lab, but what I've got is my person standing up on a high cliff. Yeah, my people do look pretty awful. And as this person jumps down, their gravitational potential energy is being turned into kinetic energy. Then the elastic starts kicking in and they start slowing down as we get the kinetic energy being turned into elastic potential energy. And eventually the person reaches a point where they can't go any further, and the elastic potential energy is turned back into the kinetic energy, which is turned back into energy of height, which is potential energy, and then the system works all over again, and gradually energy is lost. And where's the energy lost? Well, typically as heat in the elastic. You'll also have air resistance and various other things, but the energy is slowly lost. But it's not lost. It's just changed. We can't see it. And that's why we describe it as being lost. So we see gravitational potential energy turning into kinetic energy, into potential energy, into kinetic energy again, and gravitational potential energy, and eventually into heat. So we need to have a look at energy and work. And to do this, we're going to have a look at a little experiment. And I'm just going to move and look at that one for you. What we've got here is a little box. The box contains some weights and it's connected to a Newton meter. And as I pull this, we're up to now about 1 Newton. When I get to about 1 Newton, the box starts to move, and I'm pulling this with about 0.65 newtons moving it along. Now we can change the way this system works by altering various things. So the first thing I can do is I can alter the mass. So what do you think is going to happen if I double the mass? So instead of having 300 grams in there, we put in 600 grams. So if we now pull this and it's got 600 grams, then instead of pulling this, we've now got 1 Newton worth of energy, 1.25, 1.5, it's still not moving, 1.75, and around about 1.75 it starts to move. And once I can get it moving, I can pull it at a constant rate using less energy. Let's just do that. And when I pull it now at a constant speed, it's using about 1.25 newtons worth of force. So we've got force being applied to my object and it's moving a distance. And if we look at our idea of the system, we can see that work done is the force applied times the distance moved. As a note to ourselves, we'll remember to put a better microphone on for next time. Right. Now, what happens here in this system if we change the box a little bit? And what I've got for this box is I've got a piece of rubber. And what I'm going to do with this piece of rubber is I'm going to attach it to the bottom of the box. Things never go properly when you're trying to do it in a hurry or when you're doing it on camera. So I've got my pieces of rubber here and I'm trying to hold it so that the elastic bands are not on the flat piece. So they're my elastic bands holding my piece of rubber there, and I've got my Newton meter ready to pull. Now if I pull this time, the friction is so much that it's beyond what this Newton meter can cope with. So I need to put that one aside and pull in a more powerful meter. And I'll read out the readings. We've got 2 newtons here worth of force, 2.5, 3, still no movement, 3.5 just starting to go, and it's going at 3.5, probably actually nearer 4 newtons, pulling it along. So I've changed the system by increasing the mass, but we've also now increased the friction. And so I can now pull this along at about 4 newtons. What happens if we change the scenario? Well, we can do that. And what we're going to try and do is we're going to put some washing up liquid down here so we can see what happens. So we're just going to put a little squirt of washing up liquid down here. Right, so we've got some washing up liquid. I'm going to just put this piece of rubber on that, and now we can try to see what's going to happen. And at 3 newtons, nearly 3 newtons, is about 2.9 newtons. This is starting to move. It's actually then got to 4.5 or 5. Oh, there it goes. And it suddenly went onto the slipperier surface. Also pulling my elastic band off. Let's try it again. Yeah. Well, the experiment worked once, and it's gone on to the rubber on the inside as well. So if we reduce the friction, we could see that it did go down slightly before my system came and fell to bits. So this now moves incredibly easily on here, whereas before it moved with great difficulty. We'll just try it again once more just to see if we can get it to work. So I'm just going to put this back on. Hopefully it will hold it just long enough to see if we can get it to work once. When we make videos, we can take a few takes. When we do this live, of course, you get only one chance to do it, and of course it's not going to work very well because of something called Sod's law, which is if anything can go wrong. Oh, that's Murphy's law. If anything can go wrong, it will. Sod's law is when you try to do something, you're going to be stopped by doing it by all sorts of forces. Right, that might just about hold. It's on. It's quite slippery there. And let's see what happens. So I'm going to pull, and I'm at now 1.5 newtons, and it's moving at 1.5. So yes, it did work, but we had to have a couple of goes at getting that to work properly. So if we increase the mass, this needed more force. If we increase the friction by putting on a piece of rubber to give a much sort of grippier system, then it's worse. And then if we change this to be virtually frictionless by putting some washing up liquid down, then we've got a system whereby there's virtually no friction. I do a very common experiment with many of my students, and what we do is, I'm just using a tissue to wipe the stuff off my hands. I get them to rub their hands together. Try it. So get your hands, you rub them together, and it gets warm. Now, what happens if you go and wet your hands and you rub them again furiously? Well, you might like to try that one at home. And you find that when you do that, rubbing your hands together furiously, they get quite warm. But you do this when your hands are wet, and it doesn't work. Now, let's have a look at why that might be. So if we have a look at a rough picture of my hands probably for a surface look a bit like this. These are all my fingerprints, and they rub together with my other hand, which has also got fingerprints. And these surfaces bang against one another as one moves one way and one moves the other. And this creates a high amount of friction. And as we get a high amount of friction, we generate heat. If we look at this with the system we've just looked at, with washing up liquid in there, or your hands with water, then what we've got is this surface, but now it's filled in with a liquid. And if I look at the other surface, that too is filled in with a liquid. And as they move over one another, the liquid allows them to glide easily. So now there is a low amount of friction and, of course, no heat. Friction can be our friend, it can be our enemy. If you've got your bicycle and you want to try and ride your bicycle, and you certainly don't want to ride this sort of bicycle that I've got here, then what we need to do is to have a large amount of friction between the wheel that's being driven and the road surface. Here, there's going to be a lot of grip, and the wheel is going to allow the bicycle to move forward. If we do exactly the same experiment, but we do it on ice, then the friction's going to be low, there's going to be no grip, and you're not going anywhere. Also is true when you're trying to stop, and if you know how brakes work on a bicycle, we have two brake blocks and they move in and squeeze on the tire. And of course, this gets hot, and that's how it breaks. If you want to, if you take your brake blocks and you decide to put washing up liquid on them, or grease, or oil, then when you squeeze the brakes together, there will be no friction. And, surprisingly, the bike won't stop. Because it's the brakes squeezing against there, creating friction, that is stopping the bike, and the energy of movement is being turned into heat. So we get this idea of friction being simply when two things rub together. So we can say that friction, it's when two surfaces rub together. When they rub together, we get heat generated. If you reduce the friction, then you reduce the heat generated. And it's objects pushing together that causes the friction. Now, if we look at the formula that I mentioned when I started moving that little box with the Newton meter, and we pulled it, what we've got is simply a mass here, and we've got a distance moved. So what we want to do is apply some force. So we know that work, and we're going to measure work in joules, is going to equal the force that we're going to apply, and we measure the force in newtons, and we multiply that by the distance that we're going to move, and the distance we're going to move is measured in meters. So if we take our little scenario that we had before, that I had a maximum force of 4 newtons, and I multiplied that by the distance I moved, and we'll pretend we moved it 1 meter, then I've actually achieved only 4 joules of work done, which is not very much really. We can summarize all of this in sort of a little diagram, which I'm going to draw for you. Now, this idea you'll see in the books, and what I've got is a simple scenario whereby someone is going to try and lift an object. Now, if I lift a mass of 1 kilogram through 1 meter, so our work done is going to be simply our force times our distance. If I've got 1 kilogram, this is going to have a force going down on it of gravity, and that gravitational force is going to be that of 9.8 meters per second. We're going to simplify that to make my maths easier. I'm going to call that 10 meters per second. So I've got a force here of 10 newtons. 10 newtons move through 1 meter. So my work is going to be 10 newtons times 1 meter, which is going to give me 10 joules of work done. If I instead lift this object not 1 meter, but 2 meters, then I will have done 20 joules of work. But in the same way, if I picked up 2 kilograms and my 2 kilograms multiplied by 10 meters per second is giving me a force of 20 newtons. So now if I multiply that, my work is going to be 20 newtons times the 1 meter, which is going to give me again still 20 joules. So it's not going to matter whether I lift 1 kilogram through 2 meters or 2 kilograms through 1 meter. I'm going to do exactly the same amount of work. So I was having a problem, but you didn't see that. Right, okay. So the last little bit I want to look at is we talked about gravitational potential energy. Now, this is the energy, if you like, of height. And let's see how we can do this. Energy of height is going to be gravitational potential energy is going to equal the mass that I'm going to lift up, like this rubber, the force of gravity, and the height, mgh. Well, mg we've just been working out. This is the mass times the force of gravity. So if I have 1 kilogram and the force of gravity is going to be 10 meters per second, and I lift this through 2 meters, this is going to be 1 times 10 is 20. Sorry, 1 times 10 is 10. 10 times 2 is going to give me 20. So we are going to have 20 units of potential energy. And what are those units going to be? Well, we know that our kilograms times our meters is going to give us newtons. So this is measured in Newton meters. So we've got this unit of energy, gravitational potential energy, in Newton meters. Let's see what happens when we let go. Well, when we let go, what's going to happen is my block that I've raised is going to fall. And my gravitational potential energy is going to be turned into kinetic energy. So let's have some gravitational potential energy. And we had 20 Newton meters of gravitational potential energy. This is going to be turned into kinetic energy. And kinetic energy is given by the formula half mv squared. So let's see what's going to happen here. Well, my mass is still the same. So if my mass last time was 1 kilogram, then it's still got to be 1 kilogram. We've got that times a half, so I've got a half here, times my velocity squared, and that is going to equal the same amount of energy as we started with, because energy can't be created or destroyed. So if I've got 20 Newton meters worth of energy at the start, I'm going to have 20 Newton meters of energy at the end. So let's see if we can work out what my velocity is going to be. So let's rearrange this formula. So I'm going to put a 2 up there. So I've got to have 2 times my 20. And then I'm going to divide that by my mass, which is 1. And then what I'm going to need to do is I'm going to need to square root my answer to get my velocity. So 2 times 20 is going to give me 40, over 1, which is going to give me 40, and we get the square root of 40 equals v, and if I do a little bit of a calculation, we can find out that the answer is going to be about 6.32 meters per second. So we can work out these calculations quite easily. We'll do some more of those in the next video. And we'll also have a look at elastic potential energy in a spring, which is called Hooke's law. So I hope to see you next time when we'll have a look at a little bit more in the physics. Until then, keep safe, and I'll see you next time. Bye-bye.